So 3.5 is going to be on optimization, and it's pretty much exactly what it sounds like. It's optimizing something, making something like making the volume as big as possible with a small surface area, or minimizing cost, or something in terms of that. So that's the last application for this unit. And I'm just going to start by just sharing with you kind of the steps. So these are going to be word problems, and we're always going to start by drawing and labeling a picture. Then we're going to write equations, and I just say equations. Sometimes it's only one, but sometimes we're going to write two equations, and one will substitute in the other. So we need to make sure that the equation in the end that we're going to be differentiating to find the critical values is only in terms of one variable. So with this one right here, you need to make sure in the end you have whatever equation you're optimizing, whatever you're maximizing or minimizing is in terms of one variable. Okay, whatever equation that you're going to end up using there. Find critical values. So we've been talking about critical values for this entire unit. So when you're finding the critical values, you're going to find your derivative. And then you're going to set that equal to 0 and solve from there. And then just make sure you answer the question in the end. So draw and label a picture, write equations, make sure that you get an equation in terms of one variable, whichever one you're maximizing or minimizing. You're going to find your critical values, which means you find your derivative and you set that equal to 0. And lastly, make sure you answer the question. So I have just a couple examples for you. So the first one's pretty simple. Find two numbers whose sum is 20 and whose product is as large as possible. So I'm going to start with my two numbers, x plus y, and we know that that has to be equal to 20. And then it also says whose product is as large as possible. So the product I'm going to call P, x, y, and P is what I am optimizing. That's what I'm going to be taking the derivative of. That's what I'm going to be finding the critical points of. The problem with P right now is it has two different variables in it. It has x and it has y. So what we're going to do is we're going to use this first equation over here to solve, and it doesn't matter which one you use. I could say y is equal to 20 minus x. And then I'm going to take that and plug that into the equation over here that I'm going to be maximizing or taking the derivative of. So P will be x, and instead of y, I'm going to write 20 minus x. Now I'm going to keep going with that and write that as 20x minus x squared, because I know from step 2 on the previous side, I'm going to be finding critical values next, which means I'm going to be taking a derivative, and I would rather take a derivative of a polynomial than use product rule. So now I'm going to call this P prime, and P, again, stands for my product, is equal to 20 minus 2x. There's my derivative. And then to find the critical values, I'm going to set that equal to 0. So basically you get 20 equals 2x, so x equals 10. And if x equals 10, you plug that back into the original. So we'd have 10 plus y is equal to 20. Subtract the 10 over, and you get that y is equal to 10 as well. So what do we know? We know that 10 plus 10 is 20, and we know that that's also going to give us the product that is as large as possible. And the question said, find the two numbers. So my answer is y equals 10 and x equals 10. So 10, 10 would be my answer. Second question, this one's a little tricky. So we have a rectangle, and it's to be inscribed under one arch of the sine curve. There's my sine curve. Sine starts at the origin, goes up. Let's see, and the second time sine would be 0, would be at pi. And I'm going to inscribe a rectangle. And it will be pretty symmetrical. It's under one arch of the sine curve, and we want the largest area that the rectangle can have. So just as a side note, we know that the area of a rectangle is going to be base times height. Okay, so what I'm going to do is I'm going to call this little section right here x. Okay, now it's symmetrical, so that means that this over here is also x. And then from there, I can actually label what the base of my rectangle is, because I know that this entire distance, because one arch of the sine curve is pi. So if the whole thing is pi, this whole axis here, if this is all pi, and this is x and this is x, then that means that this section right here would be pi minus 2x, and that will give me the base of my rectangle. Now, the height of my rectangle, this section right here, well, that would be y, right? So it's where it hits the y-axis. Well, we know that it hits the axis right there. If that's x, then that means that it hits at y equals sine x. So x is my x coordinate. You plug that in. Y is equal to sine x. So that means that my area will be my base, which is pi minus 2x, times my height, which is sine x. Okay, so either way here, I'm going to have to do a product rule. So, because that's step one. Step one is to write your equations. Step two is going to be to find the critical values, which means I need a derivative. So I'm going to find the derivative, or a prime. I am just going to use product rule here because, like I said, we're going to have to use it anyways. So the derivative of the first set of parentheses will give me a negative 2 times sine x plus pi minus 2x, and the derivative of sine is cosine of x. Okay, now we're going to set that equal to 0. Let's see, I don't think anything actually works out nice. So I'm going to, just to save some time, you guys can finish up this question from here. So all you need to do is just plug that into a calculator. Yeah, I don't think there's really a very nice way to do that. You can, I would just graph it and find out where the zeros are for this function right here. The next example, this one's a very, very common example. So we have a box. We want to make a box, and the box is going to be made out of a piece of tin. In this case, sometimes it's cardboard, and it's going to be 25 inches long, and it's going to be 20 inches wide. So that's what we start with. And what we're going to do is we're going to cut congruent squares out of each one of the corners, and then we fold it up to get our box. So we're going to call this x, and this is x because they are congruent squares. And it says, how large should the volume be to make the box hold, or how large should each square be to make the box hold as much as possible? So basically here we are maximizing our volume. So I need an equation for volume, length times width times height. And then that's what I will be taking the derivative of. Okay, so the length of this box, let's talk about this side right here. So we know that whole side is 20, but I'm going to be taking out these two squares right here I'm going to cut those out so that I can fold the box up. So I don't know if you can picture this, but basically I would bend right here and it would fold up into a box. So the length would be 20 minus 2x. Okay, now the width is the same thing. So the whole thing here is 25 inches, but again, I'm going to cut out these squares. So that means that my width is going to be 25 minus 2x. And then lastly, the height. Well, when you fold everything up, the height will be just x. Okay? And then from there, you're going to take the derivative. I'm going to stop right there because I think at this point we should know how to take derivatives. You could multiply the x through, use product rule. You could multiply through again, get a polynomial. You could go to the calculator and have it do that for you. So find the derivative, set it equal to 0. Now you will get a couple of values for this one. You're going to get two. One is smaller and one is a lot larger. One will not work. So make sure you plug it in the end to make sure that the x that you get actually gives you a real value. One is going to be too large and you won't have a width anymore. Okay, and then the last one. So the last one we have is we have a 1 liter can shaped like a right circular cylinder. Now, 1 liter is equal to 1,000 milliliters. To deal with volume here. So what dimensions use the least material? Okay, so we know that volume is equal to pi r squared times h, right? The area of a circle is pi r squared, right? And then times h would give you the volume, but this is what dimensions will use the least amount of surface area, or least amount of material, which is surface area. So surface area will be your let's see, that would be 2 pi r squared, one for the top and one for the bottom. And then plus the circumference, which is 2 pi r, and then that's times the height, because that's the entire think about like the label on the can. So this would be, this equation is the label and this one's the top and the bottom. Now here's the issue. This is the equation I'm going to be using because that's the one that I'm minimizing, right? Which dimensions we use the least amount of material. So I'm minimizing my surface area, but I have an R, and I have an H. So I have too many variables. So we're going to use that top equation there to solve for one of the variables, and it doesn't matter which one. I think I usually do H, but it's fine. So H will equal 1,000 divided by pi r squared. And then I'm going to plug that in. So I get 2 pi r squared plus 2 pi r, and instead of H, I'm going to have 1,000 all over pi r squared. Okay, so that's what my surface area is. You need to find the derivative. You need to take that derivative and set it equal to 0. And then in the end, you're going to have what R is, but it says what dimensions will use the least amount of material. So you'll also need to plug back into the equation to figure out what H is. And I think that one works pretty easily. So hopefully through those examples, if I can scroll back up to that top slide there, the first thing we always do is we draw and label a picture. Step 2, we write equations, and then we need to solve for one equation. Solve an equation so it only has one variable in it. Step 3 is to find your critical values, which means you take the derivative of whatever you're maximizing or minimizing, and then after that you set that equal to 0. And then lastly, make sure that you have answered the question. So sometimes it's going to say, what is the maximum volume? Plug in the values. Or sometimes it might say, what are the values? They give you the maximum value, in which case you only need to report the values. Okay, so that is it for optimization.